All right, so we are gathered here together to listen to a talk by the King of Canberra, Tristan Bice, who will talk about bundles versus Cosheaves.
Exactly. Thank you. Thank you for the intro, and well, thank you very much to the organisers for the opportunity to speak. It's great to be back in Toronto and have not just one but two conferences in sort of quick succession. So it's really nice to be here. So yeah, I wanted to talk about some sort of work in progress, basically, with a colleague of mine, Alcides Bus, basically on the kind of dualities that you can maybe get between certain bundles on the one hand and certain Cosheaves, what we call Cosheaves anyway, on the other. So it all begins, as I'm sure probably everyone here is aware, with Gelfand, right? This was the beginning of C-star algebra theory, showing that commutative C-star algebras are dual in a functorial categorical sense to locally compact Hausdorff spaces. So in particular, an important aspect of this talk is that you can at least recover a locally compact Hausdorff space from the corresponding C-star algebra, right? That C-star algebra encodes all the information you could possibly want from that space. And then the question is, well, how would you extend this to non-commutative C-star algebras? And this is something that I think a lot of people have sort of debated for a very long time, almost way back since Gelfand's time, right? What is the best way that you could extend this? And one of the first attempts, possibly one of the best, at least initially, was due to Downs-Hoffman and I think their student Varela. So their idea was basically to replace the space now with a bundle over that space. So at each point you sort of replace it with a C-star algebra. And it can be, well, any C-star algebra, but you imagine the C-star algebras to sort of vary continuously over this space. And that gives you a bundle. To make this a bit more precise, a bundle really is actually a map. It's an open continuous map from one total topological space B onto some other space X, such that each fiber is indeed a C-star algebra. The pullback of each point is a C-star algebra. And that the norm, the topology on those individual C-star algebras is indeed compatible with the whole topology of B. That's the rough idea. I mean, I could write down the axioms, but that probably wouldn't be so illuminating. The rough idea is you just want it to be compatible with the topology. And once you've got one of these bundles, well, you can again look at continuous sections now, right? Continuous maps on the space which don't map to complex numbers anymore, but to elements in the fiber of your bundle. Okay, and again, you can look at these ones that vanish at infinity, and this gives you a nice C-star algebra. But if the fibers are non-commutative now, well, that's also going to get you a non-commutative C-star algebra. And so, well, maybe it doesn't seem like you've done much, but the idea is that you've created this much bigger, possibly ugly, complicated C-star algebra from some nicer, perhaps still non-commutative, but some nicer, more manageable pieces, right? Fibers. And so your first naive question would be, can you recover the bundle, just like you recovered the space above? Can you recover the bundle from this algebra of sections vanishing infinity? And if you think about it for a second, you realize quickly, no, that's not true, even with some very simple examples. So just consider bundles over a discrete space with 2 points. So one fiber could be 3 copies of C, one fiber could be 1 copy of C, or alternatively, both could just be 2 copies of C. In the end, when you look at the sections, you get 4 copies of C, right? So these two definitely different bundles, different fibers, they give you the same C-star algebra in the end. But all is not lost. All this tells you is that if you really want to capture this bundle completely, you need more than just that C-star algebra. You need some extra data, right? What could that extra data be? Well, if you're in this nice situation where all of your bundles are unital C-star algebras, then there's a sort of canonical subalgebra you could pick that maybe might help you capture the bundle. And this is the algebra of sections, where at each point now you declare that the section should have some value which is just a scalar multiple of the identity in that particular fiber. And well, the unit is certainly central in each fiber, so that will give you a subalgebra of the center, right? With this other key property that it contains an approximate unit for this larger algebra. And so those two properties define what you might call something like a Varela pair. They didn't use that terminology, but I don't know, in the presence of Cartan pairs, maybe you might see this as some kind of precursor to a Cartan pair. So let's call this a Varela pair. And what they showed in this kind of terminology is that Varela pairs are indeed dual to these C-star bundles. That extra central subalgebra you have here does indeed give you exactly the right data you need to recover the bundle, so long as it was one of these nice bundles with unital fibers. Right? And it really is a full functorial extension of the Gelfand duality. The morphisms of the bundles were a bit complicated, but Varela did manage to do that, because you have to somehow combine continuous maps of the base spaces with morphisms of the fibers in the other direction, and there's a pullback bundle in the middle there, and so it gets a bit messy, but it does work. Right? And well, if you want to apply this theory and you have just an abstract C-star algebra given to you, well, the canonical choice for your Z here would just be to take the entire center, and that's perfectly fine so long as that center does at least contain an approximate unit for the larger algebra. If it doesn't, well, then you can always just modify things a bit. You could look at, say, the multiplier algebra. So that's unital. So the center certainly contains the unit. It certainly contains an approximate unit. And then you could apply their general theorem to say, well, I could represent the entire multiplier algebra now on some nice bundle, right? The only slight issue, I guess, is that it might be a bit big, might be too big than what you needed for A. And well, you could maybe restrict, maybe try and get some kind of duality via this, but I don't know, it would be nice if you didn't have to go through the multiplier algebra. And incidentally, this is, you might notice this is where this theorem that is often quoted as the Downs-Hoffmann theorem comes in. So I think the usually quoted theorem is that if you look at the center of the multiplier algebra, then this is really the same thing as continuous functions on the Hausdorffification of the primitive ideal space or something. But that was really just a corollary of this general work they did on bundles. Okay, so what about this? How else could we recover these bundles, right? Especially without this annoying little condition about unital fibers. Is there maybe a better or at least different way of recovering bundles even without unital fibers? Well, there is. You could notice, for example, that every open set of your base space of your bundle determines a natural ideal of the C-star algebra, namely just the C-star algebra of all those sections which are supported within that open set, right? They take zero values outside the open set. There will be many other ideals, quite possibly. Each individual fiber could contain an ideal. You could restrict the functions which take values in those ideals in the fibers. That would give you another way of creating ideals, but these are special or spatial ideals coming just from the open subsets of the base space. Okay, you'll notice that, well, if you have an open set contained in a larger one, that means the corresponding ideal is contained in the larger ideal, right? Which is the opposite to what you might be used to if you're dealing with sheaves, right? Usually you'll have some algebra on some large open set, and then you'll have a restriction homomorphism to get you onto the smaller algebra. Here we have instead an injection of the smaller guy into the larger guy. So if you look at the collection of all these ideals, all these C-star algebras, it gives you some kind of dual to a sheaf. So that's why you might want to call this something like a C-star co-sheaf. So formally, it's just nothing more than a collection of all these C-star algebras, such that whenever you look at the overlaps, you will always get some non-empty closed ideal of the large guys. And the two C-star algebra structures agree completely on those overlaps. And so the first goal, or really preliminary goal that we had in this project, was to try and show that you can in fact recover any C-star bundle now, regardless of the unitality of the fibers, from such a C-star co-sheaf, from its C-star co-sheaf of spatial ideals. And then you would like to, oh well, also you would hope that you don't even need all the open sets. Maybe you'd only need open sets in a basis or a sub-basis, so you could deal with a countable co-sheaf, and maybe that would be enough to encode the C-star algebra. And after that, we'd also like to make this a true functorial duality. Okay. But more than that, we wanted to work also with other bundles and also with groupoids, because these C-star bundles are great, but as soon as you have a non-trivial C-star bundle and you look at the sections, well, your C-star algebra will contain some non-trivial center. And a lot of the C-star algebras we're interested in, like simple C-star algebras, these have trivial center. So the bundle theory won't tell you anything interesting about simple C-star algebras. If you want to do something similar there, well, that's when you have to look at groupoids. Now, I wasn't sure of everyone's background. I mean, groupoids did already come up earlier in Mike's talk, but yeah, we didn't go through the details. So I thought just just in case, it would be good to give you a quick crash course in Étale groupoid theory and their C-star algebras. So the basic idea is that, well, if you again start from the commutative case and you want to do something non-commutative, instead of attaching C-star algebras to points in your space, you can attach some kind of non-commutative partial product between the points in your space. And this groupoid structure could then be used in a different way to get you non-commutative C-star algebras. So to define a groupoid, just quickly, so it's sort of, the best way I think is to just start off and say, well, look, I have some set, I have some partial associative products. Then you can already define units. These are just the neutral elements with respect to products if the products are defined. Inverses are just things that multiply to give units. These very important units known as the source unit and the range unit. And then a groupoid is simply one of these partial semigroups, I guess you could call it, where every element has an inverse, and moreover, the source and range units completely determine when the product is defined. That's a sort of quick definition of a groupoid. You could also say it's a small category with all isomorphisms, but I think this is it's more standard to just identify the objects and the units and just have some kind of partial product structure like this. Okay, and Étale groupoids, Étale just means you have a nice topology. Right? One where all the operations, product, inverse, source, range, they're all continuous and open maps as well. That's very important. If you're familiar with groupoids, you'll know that bisections here are very important. These are just the subsets where the source and range are injective. And you can see this already when you're defining Étale groupoids. An equivalent definition would be to say that you actually have a nice basis of open bisections, which forms an inverse semigroup in a very natural way. That you can multiply these open bisections together and you'll again get an open bisection, and likewise with inverses. Okay, so that's Étale groupoids. Examples, well, any space becomes an Étale groupoid. You just give it the trivial product, and then your entire space consists of units. So at least it does at least include all spaces, right? Groupoids, well, if you're talking about Étale, you want to make a groupoid Étale, well, an easy way to do it is just give it the discrete topology. And in fact, if you have a group, that's the only way to make it Étale. So in the setting of groups, you're really restricting yourself to discrete groups. The more interesting kinds of examples come often from group actions, which I guess is more relevant to this conference, right? So if you have a group acting on some set, you can look at these triples here. So just triples where G maps X to Y. And then you can define this partial product structure when the two middle guys agree. And you can define inverses very simply. And if X does actually carry topology, if this action is indeed an action by homeomorphisms, then it's Étale, just in the subspace topology, where X is the topology you're given and G is just considered as a discrete group. Okay, so this is known as the transformation groupoid of the action. So this is the sort of important thing. And you can also extend this to various other partial actions, semigroups, local homeomorphisms. You can get groupoids from graphs and path groupoids, things like this. The groupoids, once you're looking for them, really do appear everywhere. Okay, and we of course wanted to define C-star algebras from these. So I think again, this I think came up in Mike's talk, but yeah, the idea is you want to do things by convolution to get this interesting non-commutative product. So the value of AB at G is just the sum of the values of AJ, BK, where you look at all the J's and K's whose products are the G. Right? The only issue is this is not always defined, right? Because these sums here, they may not be finite. Even if they're not finite, we still say it's defined so long as they converge. In particular for any A or B, which is compact. The sum is finite, so this is actually defined. It's just not defined everywhere. You have to be a bit careful. Once you've defined the product, then I think the best way, maybe not the standard way, but I think the best way to define the reduced groupoid C-star algebra is to first actually focus on norms. So the first norm you can define is the usual supremum norm. Once you've defined the star operation in the usual way, you can then define the 2 norm from the infinity norm. And then you can lastly define what you might call the B norm or the finitary left regular norm. It's just the norm you would get by looking at these A's as operators just on finitely supported elements. So you do at least know then that AF, the product, is defined, although the norm could still be infinite. Right? So yeah, all these norms could be infinite on just arbitrary functions, right? So what we do is we restrict to those functions where the B norm at least is finite. And it's not completely obvious, but you can show this is actually complete. So this is already a Banach space. Even before you worry about whether the product is defined on subsets of this, you can already show that this subspace, this collection of functions is indeed a Banach space in this norm. Okay, to find the reduced C-star algebra now, all you have to do is take the compactly supported continuous functions on G, okay, and well, you know the product is defined there. You just take the closure in this larger Banach space. There is a bit of work to show that the product is still defined even once you've taken the closure. But once you've done that, it's all good. And you don't have to worry about the sort of standard way of defining things with representations, taking a closure, looking at a JMAP, you know, trying to work out if the JMAP preserves convolution, whether it corresponds to the operator product. You can forget all of that if you define things in this way. And, well, a quick example would be if you look at the reduced C-star algebra of a transformation groupoid, it is indeed the same thing as the reduced cross product of the original group and the C-star algebra defined by X. So that should hopefully convince you that the transformation groupoid and the reduced groupoid C-star is the right construction. Right, so there's your crash course in groupoids. Now we want to try and play the same kind of game we were playing at the start, right, with bundles. So your first question might be, can we recover any locally compact Hausdorff et al. Groupoids just from the reduced C-star algebra? And again, a moment's thought reveals that actually this is a stupid question, because you can easily construct examples of different groupoids. So you could have the group with 2 elements versus just the trivial groupoid with 2 elements, right? These are definitely different groupoids, but the C-star algebra is just the same. It's just 2 copies of C. Right? So again, you need to do something else. You can, well, I guess your options are basically either restrict the class of groupoids you're dealing with or add in some extra data again, or maybe both. And indeed, the usual thing to do is to first restrict to effective groupoids. So these are the ones where the interior of the isotropy is trivial. Yeah, and this immediately gets rid of all groups at least. So that means this previous example is now not relevant anymore. But with a bit of harder work, you can find other examples. I'm not sure if there are any simpler examples, but there are other examples where you have 2 effective groupoids now, and they still produce the same C-star algebra. For example, in this work of Dealey, Putnam, Strong, where they showed that the Jang-Su algebra does indeed have groupoid models for various G, even with different dimensions. So you do really need, even once you've made this restriction, you do need some extra data. And again, we get it from some kind of nice subalgebra. This time we look at the diagonal, which is just all those elements in your C-star algebra, which is supported entirely on the unit space. It won't be central anymore, but it will be commutative, and it will be maximal commutative. It will also have this nice conditional expectation onto it, you know, from the larger algebra, just by taking any function on G that's in your reduced groupoid C-star algebra, and essentially just restricting to the unit space, or officially setting it to 0 outside the unit space. Okay, so and last but not least, you can also notice that in this situation, these normalizers, so these special elements you get, which over here, which normalize the diagonal in this sense, you look A, D, A star, that always lands back in D, and likewise for the other thing. I'm not sure what happened there, but I hope everything's okay. Okay, and so all these conditions I've just said here, these define for you what's known as a Cartan pair, right? Like kind of like these Varela pairs I was mentioning before. And one of the key results of this really nice theory by Kumjan and Renaud is that any effective groupoid can indeed be recovered from that Cartan pair. So this is, again, sort of the right data you need to completely capture the G. Just this Cartan pair alone is enough. Okay, but what about non-effective groupoids to begin with? So again, we would like to get rid of this if we can. Well, again, you can play this same sort of game we were playing before with bundles. You can look at those special subsets you get from open subsets of the groupoid in this case. And in fact, it's open bisections I think you want to focus on here. So you can again look at all those functions which are supported on some open bisection O. Now, the only problem is this is no longer a C-star algebra. It's no longer closed under multiplication with itself, right? It will still be a subspace. So, but not a semigroup anymore. So it's not a C-star Cosheave in any sense, right? It's not even a semigroup Cosheave. On the other hand, if you look at two perhaps different subspaces determined by different open bisections, well, this will land you in yet another one of these subspaces, the one determined by their product. So what that tells you is that, well, if you really want a semigroup, you can obtain it by just taking the union of all of these guys. The only issue then is that it's no longer a subspace. You can't add any elements from these two different subspaces and expect to still land in one of these special subspaces. So yeah, you fix one thing, you have another problem, but it turns out this is actually not as much of a problem as you might think, that actually that semigroup structure alone is already enough to recover entirely that groupoid. Any locally compact Hausdorff-Étale groupoid. You don't need effectiveness or anything like that at all, right? It's, yeah, surprising that the product is really enough to get you this. So this is some work with Lisa I did a few years back. And if you want at least just the recovery part of Kumjan-Renault's result, that's sort of an immediate corollary, because they started with a Cartan pair, and when G is effective, these normalizers here actually correspond exactly to this semigroup that we were looking at. So you could look at the semigroup and then use our result and say, we can at least recover the groupoid. So at least part of it, falls out, I think, in a nice way. And there are various, sorry. I mean, it's a semigroup, right? You take two functions supported on two open bisections, right? Then you look at their product, it will again be supported on an open bisection, namely the products of those two open bisections. So yeah, so just on a multiplication. Once you start adding things, of course, then your supports won't be bisections anymore. So that's why you can't do that. But you can still multiply these things together. You can still have a semigroup. Does that make sense? Yep. Okay, yeah, and there were other results by, for Hannes, for example, and Eusebio, and like various other people, which I think, at least in part can be sort of obtained in a similar way by sort of focusing on the semigroup, really. I mean, you might have to go to some effort to recover the semigroup from, say, the diagonal, some other kind of structure. But once you've got the semigroup, well, then you can recover the groupoid. Okay, so what I kind of glossed over, I guess, is that the groupoids alone are not quite enough to give you all of these Cartan pairs, right? You actually need these extra little twists, right? If you really want to get a nice bijection, at least, between Cartan pairs on the one hand and effective Étale groupoids on the other, right? A locally compact Hausdorff still, of course. Okay, so yeah, this was really more of the full strength of their theorem, and that it is, I mean, I'm sort of averse to quite call it a duality. It is a duality at the level of isomorphisms, right? If the groupoids are going to be isomorphic if and only if the corresponding Cartan pairs are isomorphic, but they didn't quite have any other, they didn't look at more general C-star homomorphisms like in the original Gelfand duality, right? So it's not quite a fully fledged duality in that sense. Okay, and I don't want to tell you exactly what twists are, because I'd rather prefer to work with Fell bundles, so even general Fell bundles, right? That's because if you start working with Fell bundles, well, it's easy to also include these original C-star bundles, for example, that we were talking about before. So I don't want to get into the nitty-gritty of how to define a Fell bundle, but I can give you at least the idea. So it's like a Banach bundle. It's a bundle of Banach spaces in this sense we were talking about before. This time now, though, it's over an Étale groupoid. And you want now this B here, this total space, to also carry some kind of partial product structure, just like the groupoid. And I want this partial product structure of the total space to, in some sense, be compatible with all the other structure you have there. The partial product of G, the norms, the sums, and everything like that. I want it all to be compatible. That's, if I were to write down the axioms of a Fell bundle for you, that's really all those axioms would be saying, that you have this nice compatibility. Yeah, as I said, this includes all C-star bundles. C-star bundles are exactly the Fell bundles over trivial groupoids, where all elements are units. And twists are basically the same thing as Fell line bundles, right? With these just Fell bundles where every fiber is one-dimensional. Although I think you have to be a bit careful here. I think you have to restrict to continuous Fell line bundles. So normally when you're talking about Banach bundles or Fell bundles or C-star bundles, you only assume that the norm is upper semi-continuous on the total space, right? That's usually enough, and that's usually what you want if you want to get like a nice dualities and things like this. But I think here you have to assume a bit stronger that the norm should be continuous if you want this equivalence with twists. But yeah, this is something I've just been sort of realizing recently, so I'm not 100% sure on that. And so again, if you kind of make this assumption on the Fell bundle, like the assumption we made before on the C-star bundles, then you can again extend their work. You can again sort of bundle a lot of this work together, if you excuse the term, in one big theorem. So let's assume that we have a Fell bundle now where every fiber contains a invertible element. So in particular, every unit fiber contains a unit. Every unit fiber will be a unital C-star algebra. So it's the exact direct analog of this condition we needed on C-star bundles before. Well, then you can use this bundle to define what I call a structured C-star algebra. So it's a quadruple now, using all of these various C-star algebras and semigroups that we've been talking about before. The whole reduced C-star algebra, the semigroup consisting of those sections supported on open bisections, those sections supported on the unit space, and those sections supported on the unit space, but also taking values which are always scalar multiples of the unit. And so it's more data than you would like, but I think this is sort of the minimal data you need to be able to recover the entire Fell bundle, right? And so this is the result in the end, that you can indeed get a fully fledged functorial duality now with respect to the right kinds of morphisms between these quadruples, these structured C-star algebras on the one hand, and Fell bundles satisfying this annoying extra condition, right? Okay, so it does include the previous work, because if you're dealing with the Varela-Downs-Hoffman situation, then oops, okay, then all of these three things will be the same, right? The whole C-star algebra, the semigroup, the open bisections are just everything if you have a trivial groupoid, the diagonals, everything. The only extra data you get is from this central diagonal. On the other hand, if you're dealing with the Kumja-Renaud situation, then these two are the same because you're dealing with line bundles. This you can view as not the same exactly, but you can extract it from this by normalizers. So you can sort of forget about this, these two are the same, and then you have a pairing basically of this and this, right? So in those two situations, they reduce to pairs, but in general, you need these quadruples. Okie dokie, but now there's the question again, what about these bundles where you don't have this extra condition? How on earth would you recover things then? Well, so you can do exactly the same thing as we did before, where you look at open subsets, in this case, open bisections, right? So look at all those subspaces you get now of sections supported on some open bisection. Yep, as before, it's a subspace, it's not a semigroup. You can again take unions to get you a nice semigroup that will still allow you to recover the underlying groupoid, the base groupoid. So that's great, but really we want to capture the whole bundle, right? Just like we were talking about before with Downs-Hoffman, right? So then, okay, that's when you really need to start doing something else. So this is when you would define something like a Fell Cosheave, let's say. So this is nothing more than a family of Banach spaces now, where you have an indexed over some inverse semigroup, like the open bisections of some Attal groupoid, for example, where if you look at these overlaps, these intersections, they again, the Banach space structures agree, they're closed subspaces of the larger BS and BT, and they're non-empty. They contain zero at least, right? And it's a closed subspace. So this is how we would sort of abstract away this structure. And this already has essentially been considered by people like Excel and Ralph Meyer and Bartosz Kwasniewski, for example. So Excel called these things bundles over inverse semigroups. He defined them in a different way for starters. Also, bundle didn't quite seem appropriate here because the indexing set is an inverse semigroup. It's not a topological structure really. It's a more order theoretic structure. So I think maybe Cosheaves is a slightly better thing. But in any case, and this was really the sort of the motivation here, was that Excel and these other people had looked at these, what they called inverse semigroup bundles. They showed how to create C-star algebras from them. However, it was quite non-trivial to do that, right? It's not a simple case of just generalizing Fell bundles over Attal groupoids. However, they would say, oh, but it's worth it. It's worth going to this extra trouble because these inverse semigroup bundles are more general structures that might be useful. But I would always see this, and I would always wonder. I think Alcides as well would wonder. You know, how much more general is it really? I mean, is there perhaps a way to take one of XL's inverse semigroup bundles, first represented as just as a fell bundle over an Étale groupoid that we're more familiar with, and then just do the standard construction of a C-star algebra? Maybe that would save them a lot of hassle of defining the C-star algebra directly from their inverse semigroup bundles in a somewhat involved way. Maybe that's the way to go. So this is really what motivated the whole project that we started like a few months ago. So this is this is the goal, right? So show that you can recover any fell bundle directly from this fell Cosheave, even one of these bundles where you don't have invertibles and fibers or whatever, and maybe even when you're dealing with some countable, you know, sub-Cosheave where these open sets only form a basis or a sub-basis for the base space, and then build it up maybe to a true functorial duality as well. That would be great. That's sort of the ultimate goal. But this is work in progress, and just to start with, we were looking at this and going, well, we already have to live with the fact that these are no longer C-star algebras. These aren't C-star Cosheaves. We have to live with the fact that these are just subspaces, Banach spaces, which sort of overlap in a nice way. And so that made us wonder, well, maybe it's better to actually just focus on the Banach space stuff, right? Try and get a duality between Banach Cosheaves and these bundles, these Banach bundles. You know, could there be some non-trivial theory there? At first, I was not so optimistic that you could do much just at the Banach space level, because I was used to dealing with at least a semigroup, right? In this previous work with Lisa, for example, it seemed like the product structure is what was all important to recovering the groupoid, etc. So I thought maybe, you know, at the Banach space level, surely this is not enough structure to do anything. But it turns out there is already some non-trivial stuff you can start to say, right? So this, just for the last little bit, I wanted to give you a brief outline of where we're going, what we're doing, and how we're doing it. So the idea now is just for the moment to focus on the Banach bundles versus their Cosheaves. The Cosheave being, again, just collection of Banach spaces where they have non-empty overlaps, the Banach space structures agree, etc. on overlaps, right? So a very simple kind of structure. And you could view this, it's sometimes useful to just take the union and view this as a single thing, which is kind of a partial Banach space, right? Addition is only partially defined. And again, the primary motivation comes from these Banach bundles. You look at the sections where for some O, perhaps in a sub-basis, you look at all those sections which vanish outside the set O. But of course, it includes other more abstract situations. For example, you could take a C-star algebra, just look at its Cosheave of all of its ideals. It's usually a good little test case to look at. You could also maybe look at these things you get from inclusions, these C-star inclusions, for example, Cartan pairs, but also more general things. And you look at what Excel called slices, which turn out to be quite important to his theory on non-commutative Cartan C-star algebras. So that again would be, you know, a natural example of a Banach Cosheave to look at. Okay, so we want to try and recover these things. So first we want to recover the base space. How do we do that? Well, it helps to introduce this cover relation you can define on any abstract Banach Cosheave. Right? So you simply say that one element A of my Cosheave is covered by some collection of elements, precisely when every element in A can be obtained from, well, at least as the closure of the sum of some finite collection of sets in this intersection here. So here, I mean, you'd like to just take sums in C, but you can't take sums in C because they may not be defined. So that's why you have to first intersect with A and then take sums so that they're actually defined, right? And the idea is that this cover relation should encode covering of the open sets, at least if it came from a concrete Banach bundle. And that is indeed the case, that this relation holds in the abstract Banach bundle if and only if you know, this O here was completely contained in the N, if you're taking these from open subsets of the Banach bundle. Once you know how to encode at least covering of a single element of your Cosheave, well then total covers are just things that cover every single element of the Cosheave. That's fairly standard. And again, this corresponds to what you would expect in the case of bundles. Then you want to recover the points, right? We've recovered the covers, I guess, of our space. How do you extract points from that? Well, a point can be identified with its neighborhood filter. And a neighborhood filter, right, open neighborhoods, they have to include at least one element from every cover. So that suggests maybe in the abstract setting, you define a point as something which selects an element from every cover. And so that's exactly what we do. It turns out you want to be a bit more restrictive to get a nice space, which is at least T1. You want to look at just at the minimal selectors. So that's how you define the space from an abstract Cosheave, right? And the basis, the way you define the topology is just by looking at all the minimal selectors containing some fixed element of your Cosheave, and just look at the topology those open sets generate. Okay, and the key point though is that this is the right space to construct, in the sense that if you start with a Cosheave, then for each point you can look at this S of X, and you can look at the corresponding Cosheave, the sub-Cosheave, I guess, the collection of elements in your Cosheave, and that will indeed be a minimal selector in this sense, and that the map you then get will indeed be a homeomorphism. So in that sense, this abstract construction does indeed recover the space that you started with. Yep. These are finite what? Are they finite covers? No, actually, like that's, I mean, if you're dealing with just bundles over compact spaces, then yes, I guess they would be finite covers. But you can deal with locally compact things. You don't even have to deal with locally compact things. I mean, I'm assuming for simplicity in this talk that everything is locally compact Hausdorff, but you can actually, with a bit of care, do things even for non-locally compact things where you would have these definitely infinite covers in general. So yeah. Yeah, I mean, well, yeah, it is the closure, right? So yeah, you're allowed to take finite sums, but getting closer and closer to your A. So yeah, that's true. Yeah. Okay, so that's sort of part of the construction. You've reconstructed the base, but then you want to actually reconstruct the bundle, right? And actually, to do that, it's useful to at least analyze these Banach Cosheaves you get from bundles a bit further, to at least extract one extra condition you need to even build the bundle to begin with. Okay, so what do you do? Well, you'll note that, you know, in general, you have a Banach space, you have some subspace. You can always look at the quotient norm, right? And these turn out to be quite important here, because if you look at some Cosheave obtained from a bundle, and you look at these corresponding quotient norms, you'll see that they have a concrete interpretation, right? That if you looked at, say, the intersection of these guys, that it would be the supreme norm just on the complement of one of these guys, of the M. So it's independent of the O in the end, which is somewhat surprising. It sort of says that when you're taking these quotient norms, it doesn't matter what larger space you calculate the quotient in, because you always have to take the intersection with the larger space first before forming the quotient. And this says that, well, it doesn't really matter which one you pick, which is something special if you think about it. It's not going to happen for an arbitrary Banach Cosheave, right? And you can extend this to infinite sums, so you end up with this condition that we've just called idyllic. So yeah, it's in some sense saying that that these semi-norms you get, it really is independent of whether it's A or whether it's A intersection with C or some finite sum of C's or whatever. So it's probably maybe a bit hard to digest quickly, but let me give you some examples. So the Cosheave of all ideals of a C-star algebra is always idyllic, hence the name, right? But if you try to extend it a little bit further, then it fails, right? If you look at all hereditary C-star subalgebras, even of just M2, where you're just dealing with projections basically, then that will not be idyllic. Right? So this is a key property, because it allows you to now define a kind of quotient norm independent of the larger space in which this little a sits. Right? So it turns out if it's idyllic, then we can define this special kind of semi-norm like so, independent of the particular a you pick over here. Right? And using that also, you can use this idyllic property to define this relation. I mean, I guess you don't need it to define the relation, right? It's just saying A is equivalent to B if there's some C kind of close to both of them. But to actually show this as an equivalence, that you need this idyllic property. Okay, and the point of this equivalence relation is that it starts to show you how you can maybe recover the total space. Because if you were to start with some point, if you start with a Banach bundle, you look at this, you know, minimal selector coming from a point in your base space, right? And you then, well, look at the complement of that, the equivalence relation associated with that, then A will be equivalent to B if and only if A and B have the same value at that point X. So that suggests that if you want to construct the bundle now from an abstract Cosheave, you define the points to basically be these equivalence classes, right? Modulo equivalence classes for each single point, there'll be a different one, because you know each fiber could be different. And okay, so this allows you to define what we call this spectral bundle. So you start off with some idyllic Banach Cosheaves. You look at these equivalence classes here, although for technical reasons, it's sort of good to keep track of the minimal selector you started from. So you view these as pairs to begin with. Okay, and then so then what do? You look at this, you look at the equivalence classes, great. What topology do you put on it? Well, you put on the natural topology you would think of if you're really imagining these A's here to be some kind of section. So an open set, if you have a section, an open set could be formed by just taking a kind of open tube around the image of that section, at least restricted to some open set of the base space. That's the rough idea here, right? And you have to check various things that you can indeed have Banach spaces in each fiber. You get well-defined operations, sums, etc. Okay, and then the bundle map, which is really the bundle. Well, it's just the natural projection onto the actual minimal selector forming your space. Okay, and the point is that if you start with the Banach bundle, this construction from the abstract Cosheaves you get will indeed recover the bundle you started with. So in that sense, it's the right one, and we can at least recover Banach bundles from the Cosheaves. It does encode all the structure we would like it to. The only issue then is that, well, it would be nice, we would like to be able to define bundles even from these abstract Cosheaves, right? I guess I claim that this is a bundle, but actually, in this theorem at least, we only know it's a bundle because you started from some bundle to begin with. You would like to be able to show that these conditions hold even for an abstract idyllic Cosheaves. Turns out you can't quite do that. This is where you need some more conditions on your abstract Cosheaves to really say, oh, this is a true Banach bundle. So there are these conditions. I guess I don't want to go into too much detail. Like extensive just basically says when you're looking at these semi-norms that you can enlarge Q to these other nice subsets, which in some sense include the open sets that would I guess cover the points of the base space where A takes small values. This is sort of roughly what it's saying in an abstract setting, but yeah, I don't want to again go into details. You define these other norms. This is, in some sense, the complement norm that you get from these guys. Complement in the sense that, remember, before our semi-norms really were supremum norms, but over the complement of O. So here we actually isolate O, again using these covers. And again, this norm at M is the same thing as the previous semi-norm at the complement of M. So yeah, again, it's a complementary kind of semi-norm. There's this smoothness condition, which says these new norms, these new semi-norms we've constructed are indeed quotient norms of the original norm structure. For example, like a good test case, look at all the ideals of a C-star algebra. They are smooth in this sense, which follows from a fairly simple fact, although I'm not sure I've seen it written down anywhere, and that is that if you had some random collection of closed ideals in your C-star algebra, and you were look at the supremum or the corresponding quotient semi-norms, then actually that would be the same as just looking at the quotient norm of the intersection of all those ideals. We had a proof of this using open projections, which seems like overkill. You could probably prove it using the correspondence between like ideals, open subsets of the primitive spectrum, but even then, I don't know, it feels like there should be a simpler proof of this simple fact, which may be in the literature buried somewhere. And there's this last condition about being co-supported, which, yeah. The point is these are all fairly simple conditions or you can define on your collection of Banach spaces, right? That they're all satisfied when you start with a bundle and you move to the Cosheaves. These conditions are easy to verify. And in general, these conditions allow you to actually construct a true Banach bundle, right? One which is, one which you can represent the actual, the Cosheaves you started with, I should say, the elements of the Cosheaves. And just lastly, maybe point out that it's not actually automatic that the base space here will be locally compact or Hausdorff. You can add conditions if you want this to be true, but a better idea, like I was sort of briefly mentioning with Charles, is that maybe just live with the fact that sometimes you might want to look at base spaces that aren't locally compact and Hausdorff. And as long as you're careful about how you do things, then you can still get these recovery results. You can still get some kind of duality, some bijective correspondence. And yeah, as I was mentioning before, it is a good bundle in the sense that it's very easy now to represent elements of your Cosheaves as actual sections of your bundle, right? Again, though, there is an extra condition to ensure this is a faithful representation. But yeah, I think we've basically nailed down the conditions we need to get this nice duality between Banach Cosheaves and Banach bundles. And at the moment, we're just thinking about exactly how to extend this now to the original things that motivated us, which were these fell bundles over a tile group length. So that's it.